All right, so this corresponds to the lecture of the 6th, from the 6th of March. That would be Wednesday. Yeah, Wednesday the 6th of March. And one of the things that I wanted to, or what I talked about at the beginning of this lecture, was the kind of arc of the semester. So we started out and we were talking about sugars. We used sugars as our way to segue into a discussion of nucleic acids, because if you know what a sugar looks like, then it's easy to kind of construct what a nucleic acid or a nucleotide looks like, because a nucleotide is at least one phosphate group, a nitrogenous base, and finally a sugar. So we talked about that, and whenever we talked about that, that was our way to then talk about, well, DNA to RNA to proteins. So we use that as a segue to talk about amino acid structures. And then we have just finished kind of our discussion of protein structures, the different orders of structure, and finally now we're at a point where we can talk about function. And the protein that we're going to use as our discussion for function is hemoglobin. We're going to talk about hemoglobin and myoglobin. These are oxygen binding proteins, and these serve as a great model to represent protein function discussion. Now keep in mind, this is just an example. So if you understand how hemoglobin binds to oxygen and some of the phenomena that you observe with that, then you have a greater understanding of, well, protein ligand interactions. All right, so we will go ahead and get started on that right away. So hemoglobin and myoglobin, these are two different proteins. They both bind to oxygen. Now, there are structural similarities and there are both structural differences. The first thing is that they both bind to the prosthetic group heme. Heme is a ringed structure that in the center of it is an Fe2+ ion. Okay, so that Fe2+ ion coordinates binding O2. Okay, so that's a similarity between them. Structurally, they look fairly similar to one another, but one fundamental difference is that myoglobin is a monomer. Hemoglobin is a tetramer. Now, hemoglobin is also referred to as a dimer of dimers. So an alpha beta subunit, that would be one dimer, and then another alpha beta subunit that makes your other dimer. So that's one thing to keep in mind. Now, whenever we were going through our early discussion of hemoglobin and myoglobin, what makes them different and what makes them similar to one another? So we've already talked about what makes them similar to one another, as well as a little bit of what makes them different from one another. Now, what I wanted you guys to really take away from this first day's lecture was, what does the overall, what's the impact? I guess, what's a visual that you can take home from this? And what I chose to do is I chose to talk about binding. So a hemoglobin and a myoglobin binding curve. Okay, so a hemoglobin and a myoglobin binding curves, they will have basically the same appearance. On the y-axis, you look at YO2. And so that is the percent saturation of oxygen in all of the oxygen binding sites. And you have a scale from 0 to 1, 1 being 100%. On the x-axis, we have concentrations of our substrate, or concentrations of our ligand, which is O2. Now, you can correlate O2 concentration, since it is a gas, with PO2. And that's going to be measured in torr. So what is the pressure of this gas in a given environment? Now, there was a very significant point on this curve, and that is the 0.5 point. So what's your 50% saturation point? Your 50% saturation point is, well, when we look at something like myoglobin, let's say that you have 100 molecules of myoglobin. There are going to be 100 binding sites for O2, and you would reach that 0.5 when 50 of those 100 binding sites are occupied. Now, what's significant about this is where does that relate to our concentration of O2? So how much O2 do you need in the environment to reach that point? So let's go ahead and label our x-axis 10, 20, 30, 40, and 50, 60, and 70. Okay, now I'm going to draw a myoglobin binding curve, and it would look a little bit like this. It's going to at some point basically plateau out, but when you look at this and when you evaluate myoglobin, one of the things that you want to do is pinpoint where that P50 point is. So we dot that down, and let's say that's about 8 torr. So what that tells you is you need an environment that has a concentration of 8 torr in order for myoglobin to reach 50% saturation. Okay, so whenever you compare that to another myoglobin binding curve, say that looks like this. Let's say we have a mutant myoglobin that it looks a little bit like this. What does that myoglobin binding curve tell us? And I apologize for any sort of unexpected curves there, but this tells you 15 torr. So what does that ultimately mean? That means when we compare, let's call it protein A and protein B. So myoglobin A and myoglobin B, when you compare those two different proteins to one another, you can ask yourself the question, which one requires less O2? So which one would survive or be functional in a low oxygen environment? Well, that would be protein A, due to the fact that it needs less oxygen to reach 50% saturation compared to B, which needs a concentration of 15 torr. So you see the same thing with hemoglobin that you see with myoglobin. You see the shifting of the curves from a stated position to the right or to the left. Now, what I want you to know about this is I want you to know how the movement of that curve affects the protein's ability to bind oxygen, or basically look at that as, is it good or is it bad? And it's easy to look at this as good or bad because we need oxygen to survive, and so if you need a lot of oxygen to reach 50% occupancy or 50% saturation, that's not quite as good as where you need a very small amount of oxygen to reach 50% occupancy or 50% saturation. So that's kind of the key points of myoglobin and hemoglobin. Now, if you compare that to, that's simply from the binding curves. What is important to recognize about these is what's the fundamental difference between hemoglobin and myoglobin? Hemoglobin has 4 binding sites. So if you have 100 copies of a hemoglobin protein, you have 400 oxygen binding sites. Myoglobin is not as good at carrying oxygen as hemoglobin. Hemoglobin can carry much more oxygen. It can carry 4 times as much oxygen. All right, so we continue this discussion a little bit further on the 8th, and we're actually going to pick it up in class on the, I guess that would be the 11th? Yeah, the 11th and 12th before the final, or before the exam on the 15th. No, 11th and 13th. But protein function is basically the last piece of material that we're going to be discussing for this, this next exam. Anyway, I hope this was helpful. We're going to, in the next few discussions, we're going to detail why these binding curves differ based on the protein's protonation state and the protein's kind of, well, its structure. All right, well, thank you very much. I hope this was helpful. Have a good day.